It is the spring of 1905 in Bern, Switzerland. Albert Einstein, a 26-year-old patent clerk, finishes his day's work and boards a tram heading home, rolling away from the city's prominent Zeitglocke clock tower. As he rides, he imagines a physical impossibility. What if this tram were to suddenly accelerate to the speed of light? Looking back at the tower while traveling 186,000 miles per second, the hands of the clock would appear to him to completely freeze. Yet Einstein knows that for anyone standing directly under that same clock tower, the hands would continue to tick along at their normal, steady pace. To Einstein, the implication was clear. The clock tower hadn't stopped, but his perception of it had. This mental exercise suggested that time itself might not be a fixed, universal metronome, but a variable that shifts with movement. To understand how Einstein arrived at this conclusion, we have to look at a major conflict between two pillars of physics. First, Isaac Newton had long established that speed is always relative. A train travels at 40 miles per hour relative to a stationary platform, but only 20 miles per hour relative to a train running alongside it. But then, James Clerk Maxwell mapped out the laws of electromagnetism. Maxwell discovered that light is an electromagnetic wave, and its speed is locked at roughly 300 million meters per second. According to his equations, this speed is absolute. It doesn't matter who is measuring it or how fast they are moving. These two rules cannot logically coexist. If Newton's laws of relative velocity apply to everything, light shouldn't have a fixed limit. But if light truly is an absolute constant, then Newton's laws are broken. Einstein faced a choice. Either Newton was incomplete, or the speed of light was not universal. To resolve the conflict, he needed a mathematical framework that allowed both physics rules to be true at exactly the same time. Einstein engineered another thought experiment to test this. Picture an empty train platform, where two lightning bolts strike the ground at opposite ends. If you stand directly in the middle of that platform, the light from both strikes travels the exact same distance to reach your eyes, meaning you see them hit at the exact same time. Now, imagine a passenger on a train whizzing past that exact midpoint at the speed of light. Because they are moving toward one strike and away from the other, the light from the closer bolt hits them first. Here is the problem. If both people calculate the speed of the light beams based on when they see the flash, they get different numbers. That directly violates Maxwell's law that the speed of light is perfectly rigid. To keep the speed of light constant for both the stationary observer and the train passenger, something else in the entire equation has to give. Einstein quickly realized that the moving person's actual experience of time must slow down to compensate for their extreme speed. He named this mechanic time dilation, framing it within his new theory of special relativity. The math proved that motion through space and motion through time are inversely linked. Einstein recognized that time is so malleable it behaves like a physical dimension. He wove the three dimensions of space and a dimension of time together into a single continuous fabric called spacetime. This diagram illustrates how a massive body distorts spacetime like a heavy bowling ball on a trampoline. The fabric curves deeply downward. This steep slope is gravity, forcing smaller objects to roll into the valley. As an object falls deeper, the slope gets steeper, accelerating it toward the center. Because special relativity dictates that faster movement slows the clock, this gravitational acceleration has a bizarre side effect. The deeper you drop into a gravity well, the slower your time runs. To prove how this works mechanically, imagine a man falling from space toward Earth, carrying a photon clock, a device that measures seconds by bouncing a single particle of light straight up and down between two mirrors. Comparing a stationary photon clock to a falling one, observers on Earth see the falling clock's light particle trace stretched out diagonal triangles. Moving diagonally means it travels a much longer physical distance to complete a single tick. Since the speed of light cannot change, covering that extra distance takes more time. The actual duration of a second stretches out, proving mathematically that the falling man is experiencing time passing significantly slower than the people watching him from the ground. Near extremely dense cosmic bodies, this effect is massive. If you were to land on a planet in close proximity to a black hole, the gravitational pull is so severe that a single hour of your life locally could equal 7 years passing for people back on Earth. We don't have to travel to deep space to find this happening. Our own planet's mass distorts the fabric of spacetime enough to cause the exact same variable passage of time. This malleability affects every physical and biological process, from the decay of atoms to the rate of cellular aging. Every clock in the universe slows down when subjected to high velocity or intense gravity. Because Earth's gravitational pull is slightly stronger at the surface than it is a few feet higher in the air, time is moving marginally slower at ground level, which leaves us with a strange, localized consequence of living in a flexible universe. Your head is biologically older than your feet.